So hi everyone, I will present to you my work on the computation of discretization error bounds on the fatigue damage of a shear plate. So I'll start off with a little bit of context. So in the offshore industry, the structures are often complex with complex solicitations. So usually we will use discretized methods such as the finite element method to model the structure. This model is checked against several limit states, including the fatigue limit state that is very costly. This is partly because multiple C-states need to be computed in order to simulate the full deployment of the structure, but also because each simulation has to be done for approximately 3 hours of deployment. The consequence of this is that the choice of the best mesh has to be done a priori, and mesh convergence cannot be checked a posteriori. The aim of this work is to provide industrials with an a posteriori method to check mesh convergence on the damage. So about the presentation of today, I will start with classical damage analysis for jacket structure, then I will move on to discretization error estimation and the method we've developed, and finally I will apply this method to the shear plate of an offshore substation. So fatigue analysis for jacket structure is prescribed in the NV. So first you need to obtain a time series of stress at your hotspot using your FEM model. Then, using rainfall counting, you can identify within the signal stress cycles. To do so, you drop a droplet of water at each true and peak of your signal. Starting from your first true, the first droplet will fall behind the first peak, so you identify a half cycle of amplitude 2. This is only a half cycle because you're only going upward and not downward as well. So you repeat this procedure for the first peak, and the droplet of water falls beyond the second true and the third true, so you identified 2 half cycles of amplitude 3 and 4 megapascals. Finally, you repeat the procedure for the whole signal and you obtain a table like this. Then, using SN curves, you may calculate the number of cycles to failure for each stress range. Finally, using the Palmgren-Minor rule, you may calculate the damage as the sum over I indexed on stress range as the number of cycles above the number of cycles to failure, which you find equal to 0.4 in this case. So this is smaller than 1, so the structure will not fail. But it is dependent on the mesh you've chosen for your FEM model. And how can you know if this value of the damage is converged or not? So you may use the discretization error estimation on stress to do so. The error of discretization write as a norm over the displacement field of the FEM solution minus the one of the exact field. Because you don't have the exact solution, there are still several indicators of it. One is based on residuals, and basically it is impractical because you will need to compute a constant that is purely arbitrary. The second one is based on the error in constitutive relation, but this one is impractical because it is intrusive to your FEM code and may not be used for industrial codes such as Abacus or ANSYS. Finally, the stress smoothing techniques is fairly easily implemented. You only need to approximate your stress exact field by smoothing your FEM field. The problem with this error of discretization is that it is an energetical measure, and usually the output of your FEM code is on a quantity of interest S that may be, for example, a principal stress component at a hotspot of your structure. To compute this error of discretization on S, you will need S to be a linear form of the displacement field. Then what it requires is to solve an adjoint problem. So you've defined the forward problem as the first FEM problem that you've computed in the first place. And then you will estimate this error of discretization on both forward and adjoint problems. Finally, you obtain a bounding of the exact solution between S minus and S plus. So this bounding is approximate because you've approximated your exact solution of your stress field. So finally, you end up with a time series of stress at your hotspot with error bounds around the FEM solution in red. So then you will need to propagate these error bounds to the damage. And to do so, we want to compute two signals, one that is maximizing damage and one that is minimizing damage. So the hypothesis we make here is that the one minimizing damage is the one minimizing oscillation, because if you minimize oscillation, then you minimize the stress ranges, but the number of cycles you've identified as well. So in the end, you minimize the damage. So to build the signal minimizing damage, I've written in the paper a more thorough approach to implement it in a code, but a more intuitive approach is to choose the trajectory of droplet falling within each error bound at each timestamp. So you can see clearly that it minimizes oscillation. And so the second signal is maximizing damage, and to do so, we first compute the mean of the FEM solution over the whole time frame. Then we choose the signal maximizing damage as sigma m passing in each interval at the point furthest from signal's mean over the whole time frame. So this is the signal in red. So this is not the signal maximizing damage, because a signal oscillating between lower and upper bound at each timestamp of the signal would maximize damage and oscillation. However, this signal is unrealistic because the exact solution should not change drastically between two following timestamps. So we continued with the signal I've defined before. And having those two signals, the method to obtain bounds on damage is straightforward. You just use rainfall counting, palm-grain minor rule, and SN curve to propagate to the damage. So then we wanted to apply this method to the shear plate of an offshore substation. So we worked in partnership with Les Chantiers de l'Atlantique, and we chose the shear plate of one of their offshore substations as a point of interest to apply this technique. So this shear plate is connecting the pile sleeve to the jacket structure, and this pile sleeve is where the pile fixes the jacket structure to the ground. We chose this shear plate because it's at the bottom of the structure. Then wind dynamical solicitation are already filtered by the structure, so we can use a quasi-static approach to model the structure. So the aim was to compute discretization error bound on the damage of a welding toe of this shear plate. So about the workflow that we used, Benjamin Rocher from Les Chantiers de l'Atlantique ran his FEM model of the jacket structure over 3 hours of deployment in a single sea state. He obtained in the 4 tubulars bounding the shear plate the tensile stress that we used in a local approach to obtain local stress at the weld toe. So we computed the error of discretization only on this local approach, and we obtained by signal post-processing the signal minimizing and maximizing damage in order to compute SN curves and palm-grain minor rule to obtain the damage. About the jacket structure mechanical problem. So the structure was fixed to the ground at its pile sleeves, and the hypothesis was a 3D structure made of beams and shell elements. We used quasi-static approach, small perturbation, and moisture forcing. The sea state that was chosen was HS equal 2 meters, T equal 10 seconds, and the swell decomposed into 50 air waves. About the time discretization, we chose 20 points per peak waves, and the material was chosen as homogeneous, linear, elastic, and isotropic. The output was the tensile stress in the 4 nodes of the 4 tubulars. So basically, we ended up having 4 components in 4 tubulars, so 8 components of stress at nodes bounding the shear plate. So we use them as boundary conditions to a local problem of the shear plate. To do so, we interpolated them on each edge, and we removed any body motion using a punctual link and a pivoting link. The hypothesis was the same one as for the global approach, to which we added 2D plane stress. The output was the principal stress component at N0.5, so the weld toe, distant from 0.5 times the thickness E to the edge of the shear plate, which is what is prescribed by DNV. The problem with this quantity of interest is that it's not a linear form of the displacement field. So to linearize it, we added the hypothesis that because the shear plate is mainly undergoing shear, then the principal stress component will be in shear and will be directly sigma parallel, which is a linear quantity of interest. So two meshes were tested, one of 50 millimeters at the well toe, which is what is prescribed by DNV, and one with 3.3 millimeters as the well toe, which is much finer. So about the result we obtained, so here is a time series of bounds on stress at the well toe for the coarse and the fine mesh. You can see that there is no intersection between the bound on the coarse mesh and the one on the fine mesh. So if the exact solution lies within the bound, it should be at the intersection between these two meshes. Because it's not the case, it means the exact solution is probably outside the bound estimated. So here is a post-process signal on the fine mesh. You can see the signal minimizing damage in blue and the one maximizing damage in red. You can see that the stress ranges are about 1 megapascals. And if you have a look at the SN curves from DNV, it's even below what is plotted, so you will find very low damage. So these small stress ranges may be due to a sea state that was not impactful, or also because principal stress may not be in pure shear. Also, it may be because we only use tensile stress and bending stress should be added as a boundary condition as well. And finally, the shear plate may not be a critical part, the shear plate well toe may not be a critical part of this offshore substation. So we plotted the table at the bottom of this slide with the fine and the coarse mesh, the lower and the upper bound, and the FEM damage. So what you can see first is that the bound on the fine mesh is included within the one on the coarse mesh, which was not the case for stress, meaning the exact solution may lie within the bound estimated now. You can also see that there is very low damage, about 10 to the minus 14 on the fine mesh. This may be due to a single sea state of 3 hours, but also because we observed small stress ranges. So what you can see as well is that the fine mesh allows to guarantee the order of magnitude of the damage because it's in the range of 10 to the minus 14. You can see as well that there is a factor of 25 between the estimation of the damage with the FEM solution on the coarse and the fine mesh. So what we wanted to do next is to check whether the reason why we found very low damage was because the sea state was not very impactful. To do so, we wanted to simulate a sea state of HS equal 4 meters without running the full structure a second time. To do so, we started with the air wave horizontal velocity that write as proportional to the amplitude A of the wave. And the Morrison equation writes the horizontal force on the jacket structure as dependent on the velocity squared and on the derivative of the velocity. So if you approximate this horizontal force as proportional to the amplitude squared, then multiplying by 2, HS will multiply by 4 the solicitation and the jacket structure. So then if you model the structure as purely linear, it will multiply by 4 the stress at each 4 nodes delimiting the shear plate. So then I plotted on the left the table you've seen just before, and on the right the one we obtained by running only the local problem with boundary condition given by 4 times the one for HS equal 2 meters. So what you can see is that the order of magnitude on the fine mesh is now 10 to the minus 11. So as a reminder, to go from 3 hours to 20 of deployment, it's equivalent to multiplying this damage by 584 times 10 to the power of 4. So basically your damage will be in the range of 10 to the minus 6 on a 20-year deployment on HS equal 4 meters. So it means that low damage is not a consequence of a C-state being not impactful, because HS equal 4 meters should be impactful. So the other hypothesis may still be true. There's still a factor of 25 between the coarse and the fine mesh on the FEM damage for HS equal 4 meters, and the fine mesh still gives the right order of magnitude, while the coarse mesh doesn't give the same order of magnitude. So about the conclusion of this work, so this method allows to check mesh convergence on the damage a posteriori. Future work will be on multiple C-states in order to get the full extent on the full deployment of the structure of the damage. The perspective will be to use guaranteed error bounds on principal stress component and not using an hypothesis to make it linear and use a different estimation of the error bounds. And finally, we would like to use a remeshing strategy based on discretization, error reduction, and damage in order to be able to guide remeshing. So thank you for your attention, and if you have any questions, feel free to ask them.